When an undersea internet cable breaks, the first repair happens inside a network control room, where traffic moves away from the damaged route. Engineers measure the fault from land, a specialist vessel loads spare cable, and a crew sails toward a target that may be several kilometers below the waves. The cable can be thinner than a garden hose in deep water, yet finding, lifting, joining, and lowering it may take weeks. So how do you repair a glass connection on the ocean floor without making the damage worse? The first clue is usually a change in the cable system itself. A submarine cable is more than a bundle of optical fibers. Long routes also contain repeaters that amplify the light signal, along with a conductor that supplies electrical power to submerged equipment. Landing stations at each end monitor the system. When an alarm appears, engineers compare optical and electrical measurements to work out what has changed. At almost the same moment, network operators begin protecting the data. The global internet is a web of routes rather than one continuous line. Where enough alternative capacity exists, routing systems can send traffic through another cable. A message that normally crosses one ocean path may take a longer path through a different landing station. The user might notice extra delay or nothing at all. That automatic detour is not the physical repair. It buys time. A country or island served by only one or two routes has far less room to maneuver, which is why geographic diversity matters as much as cable strength. Redundancy can keep services moving, but it cannot replace a damaged link forever. Control room now needs an answer to a deceptively simple question. Where is the break? The route may stretch for thousands of kilometers, and the damaged section is invisible beneath moving seawater and layers of seabed sediment. The cable itself changes along the route. Close to shore, steel armor and extra protective layers help resist anchors, fishing gear, abrasion and movement. Far offshore in deep water, the same system can use a much slimmer, lightweight cable because surface activity cannot reach it. Inside both versions are the optical fibers, strength members, insulation, and the conductor that powers repeaters. A repair ship must carry components that can restore all of those functions, not merely reconnect the glass. Engineers can narrow the search from the landing station. In a repeated system, supervisory information can identify the affected section between pieces of submerged equipment. Electrical resistance, capacitance, and insulation measurements provide more clues. Optical reflectometry sends a pulse of light into a fiber and studies what comes back. Because the speed of that pulse is known, the return time helps estimate the distance to an interruption or abnormal reflection. The measurement does not place a bright marker on the seabed. Cable length, route geometry, test uncertainty, and movement of the damaged ends still matter. But it can turn an ocean-scale mystery into a workable search area. Engineers combine the test result with the cable route, water depth, seabed charts, and any information about recent activity near the line. Now comes the detail that determines whether the outage lasts days or weeks. A repair ship cannot simply leave the nearest harbor with a coil of generic fiber. The operator needs access to a vessel, compatible spare cable and jointing equipment, trained personnel, route records, and permission to work in the relevant waters. Weather, transit distance, customs clearance, and permits can all delay departure. This is why cable owners join regional maintenance agreements or arrange private repair coverage before anything fails. Spare cable and components are stored at strategic locations. Crews practice procedures that may not be used on a particular system for years. In cable repair, readiness is part of the infrastructure. The work package also needs the original route position, water depth profile, cable type, jointing instructions, and the location of nearby seabed infrastructure. The vessel may load several kilometers of spare cable because the damaged length and final geometry are not known exactly before recovery. Every loaded component must be traceable and compatible with a system designed to operate for decades. The International Cable Protection Committee reported more than 170 telecom cable repairs during 2025, close to 4 per week. Around 70 to 80% of faults are linked to accidental human activity, such as fishing and anchors. Natural hazards and equipment failures account for other cases. These incidents are regular enough to require an established global repair system. but each job still has its own seabed, weather, cable design and legal conditions. Once the repair vessel reaches the area, it must remain precisely positioned while working over a point far below. Dynamic positioning uses thrusters, satellite navigation, and motion sensors to hold the ship against wind, waves, and current. The crew then chooses a recovery method based on depth and seabed conditions. An exposed cable may be found or handled by a remotely operated vehicle. In other situations, the vessel tows a grapnel across the plotted route. The grapnel is not a casual hook dragged through the ocean. Different tools are selected to find, cut, or recover cable, and the ship controls their path and tension carefully. Near other cables or pipelines, the procedure becomes even more controlled because solving one fault must not create another. The damaged line may already be severed, or the repair crew may cut it deliberately after locating the bad section. One sound end is brought to the surface. On deck, technicians test it to confirm that the recovered side leads back toward the expected landing station and that the remaining fiber is healthy. The end can then be secured while the vessel recovers the other side. In a common sequence, the first healthy end is joined to spare cable, sealed, tested, and temporarily placed back in the water with a buoy or controlled holding arrangement. The ship then crosses the route to recover the second healthy end. This separates the two sides of the job and gives the crew space to remove every questionable part of the damaged section. Exact procedures vary with the cable, depth, seabed, and repair tools, but the principle is consistent. Verify each end before joining the system back together. That sounds like pulling up a rope, but deep water changes the forces dramatically. Kilometers of suspended cable have weight, drag, and a curved profile through the water. Too much tension can damage the cable. Too little control can create loops or allow it to touch the seabed badly. The ship adjusts speed, position, and cable handling machinery so the line rises within safe limits. The faulty portion is removed and replaced with spare cable from the ship. Technicians prepare the tiny glass fibers, align them, and fuse them so light can cross the new joint with very little loss. The electrical conductor and strength members must also be restored. Finally, the connection receives mechanical and water protection designed for pressure, tension, and decades of immersion. One joint is not enough. The replacement section has to connect the two healthy ends of the original system. Depending on the method, the crew may join spare cable to the first end, pay out enough length to reach the second, then make the final connection on deck. This creates a repaired section with two joints and enough additional cable to form a controlled curve or bite when it returns to the seabed. Before anyone lowers that final joint, the system is tested again. Optical measurements check attenuation and splice loss. Electrical tests check insulation and continuity. The landing stations and the ship coordinate because submarine repeaters may be supplied by high-voltage power equipment on shore. Safe repair requires the system to be isolated, grounded, and handled under a defined procedure. Only after the repaired path passes its tests does the ship lower the cable. The final bite must land without excessive tension or sharp bends. In shallow water, where anchors and fishing gear pose greater risks, a remotely operated vehicle or cable plow may bury the repaired section. In very deep water, the cable is often laid directly on the seabed because ordinary surface activity cannot reach it. The vessel cannot simply drop the joint over the stern. Engineers calculate how much cable to pay out as the ship moves, allowing the bite to settle in a broad curve rather than pulling tight between the original ends. Cable tension is monitored throughout the lowering operation. An ROV may inspect the final position, confirm separation from other infrastructure, or guide burial where the seabed permits it. Traffic can then return to the restored route, although network engineers may do this gradually while they monitor performance. The landing stations continue watching optical power, electrical behavior, and repeater status. A successful repair ends quietly. There is no ribbon cutting on the ocean floor, just an alarm that clears and a route that becomes available again. The physical joint may take hours, but the complete operation depends on decisions made years earlier. Engineers had to survey the route, record the cable design, stock matching spares, maintain ships, train jointing teams, negotiate repair agreements, and preserve alternative network paths. A cable survives a break because the system around it was prepared to fail safely. That is the deeper engineering lesson beneath the ocean. Resilience does not mean building one cable that can never be damaged. It means detecting trouble quickly, moving traffic elsewhere, locating the fault accurately, and having people and equipment ready to restore the missing link. The next time a video call crosses an ocean, the remarkable part is not only the pulse of light under the seabed, it is the repair network waiting above it, long before anyone needs to send the ship.